Hey everyone, welcome back to Calculus 2. This will be part B of the first lecture. So where we left off in the previous lecture was we had just defined this idea of the indefinite integral. Right, the indefinite integral is the operation of identifying the entire family of antiderivatives of a function f. Okay, so when I say the integral of f of x dx equals big F of x plus c, what I've done is I've said, okay, I'm interested in the function f of x. I need to know the I want to identify the entire family of antiderivatives of f, and that's this operation of indefinite integration. Okay, so operation of indefinite integration. Okay, and so we talked through that, and we had some, a very nice proof in the previous section of the fact that these families all of the members of the families have a particular form, and then what we said was integration undoes differentiation, and differentiation undoes integration. Okay, so we saw that. We saw, kind of a quick derivation of that fact. Now, this idea, we'll get into this idea a lot more in Calculus 2. A couple of lectures from now, I think maybe 2 or 3, we get into something called the fundamental theorem of calculus, which explores this idea in a lot of detail. But we introduce it pretty much on day one when we teach calculus, because this relationship allows us to onboard a huge number of integration formulas pretty much immediately. So if you recall, when we were learning about differentiation, we didn't have this luxury of like, okay, day one, we know like 50 differentiation formulas. We kind of had to work through them the hard way and sort of blood, sweat, and tears our way to a decent stack of differentiation options. But here we kind of can, given if we can recall the differentiation rule, we can kind of force out you can frequently force out a nice integration formula. So let's do an example of this. So here's an example. If I say the integral of x cubed dx, and I want to know what that is, what that's equal to, then I can, if I say to you, hey, it's x to the 4th over 4 plus some constant of integration. Why is this? How do I know this? Where does this come from? Right? Well, it comes from the fact that of this relationship here. So this guy here, this piece over here, is an antiderivative of x cubed. How do I know that's the case? Well, I can differentiate it. If I differentiate x to the 4th over 4 plus c, I get 1/4 ddx of x to the 4th plus ddx of c. Okay, and of course this is 1/4. Now what happens here? Well, when I differentiate x to the 4th, I get 4x cubed. And then what happens when I differentiate c? I just get 0. And so I have 4x cubed over 4 plus 0. So I just have x cubed, don't I? And so this is, so the idea, the definition this indefinite integral is that it's the operation of identifying the entire family of antiderivatives of a function, right? And so that's what I've done here. I've said, okay, the integral of x to the third power dx must be x to the fourth over 4 plus c, because this is the general form of the antiderivative of x cubed, right? And we can see that by differentiating it. Okay, so this is just a specific example, right? But this formula though can be generalized easily, right? We could just take the more general statement and we could say the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus some constant of integration, for the same reasons, right? For the exact same reasons, and that being that this is an antiderivative of x to the n, right? And we could demonstrate that by just differentiating it. X to the n plus 1 over n plus 1 plus c, right? We'll do this quickly. We differentiate that. Well, you get 1 over n plus 1, right? And then this derivative, just like before, you get n plus 1 times x, and then it's n plus 1 minus 1, right? That's how that works. And then this derivative is 0. And so the whole thing is 1 over n plus 1, and then this would be just n plus 1, and then n plus 1 minus 1 is, of course, x to the n. Okay, and then, of course, the n plus 1's cancel, and you just get x to the n. So that's the justification. So this would be kind of our first, maybe this is our first integration formula. And we could get a whole bunch of other ones. If you just think back to all of those differentiation formulas, many of them are easy to flip on their head. Like, for example, the trig functions. What about the integral of sine of x dx? Well, that's just negative cos x plus c. Okay. Why is that? Well, it's because the derivative of negative cos x plus c, I can think of that as the negative ddx of cos x plus ddx of c. So that's negative, and the derivative of cosine is negative sine. And then this is, of course, 0, and so you end up with just sine of x. Okay, and so this is the general form of the antiderivative of sine of x. Okay, so therefore it's the indefinite integral of sine of x. Okay, we can get a whole bunch of them like this. So we'll go through a list in a second here of all of these. But before we do that, I want to take a second to look at a few special, what I would consider kind of special integrals, or almost like properties of the indefinite integrals. And so properties and special integrals. We'll just call this out quick. Okay, properties and special integrals. So the first one is the integral of 0. What's the indefinite integral of 0 dx? Right. So, well, if you think about it, it'd have to be c. Just have to be the constant of integration itself, right? Because if I differentiate any constant, I get 0, right? And that's the only way for the derivative of anything to be 0 is if it's equal to a constant value. So that's the first one. The second thing of note here is the integral of a constant, and I'll denote that by k just to distinguish it from the constant of integration. So if I integrate a constant, what do I get? Well, what do I have to differentiate to get a constant? Well, I have to differentiate x, or some constant times x with some kind of, coefficient other than 1. And so basically, this is looks like that, right? So if I differentiate k times x plus c, I get k, right? So this would be the general form of the antiderivative of a constant k. Another one, this is a little more like a property. That's the integral of k times f of x. Okay, so if f of x is some function's integrable, k is just some constant, some real value constant, then it's permissible for me to pull the constant outside of the integrand and multiply it after the fact, right? So integrate f, multiply it times k. Right, and this, I can do this because I can do it with the derivative. d dx of kf of x is equal to k times f prime of x, right? We know that from our differentiation, right? I can pull the constant outside of the derivative, differentiate the function, and then multiply it times the constant. Similarly, we can do the same thing with sums and differences, right? So the integral of f of x plus or minus g of x, that's equal to the integral of f of x plus or minus, and I gotta put the dx on there, plus or minus the integral of g of x dx. Okay, so this is like a property that is true for derivatives, and so integration and differentiation being inverse operations, integrals kind of inherit this from them, right? And this is because d dx of f of x plus or minus g of x, well, that's just f prime of x plus or minus g prime of x, right? So we get it from there. That's where that comes from. So that's nice, right? It's good that these things hold and they're true. So those are kind of the properties and special integrals that we'll start with. And now let's look at some integration formulas. And I'll say obvious, but some of these aren't actually obvious. But they're obvious in the sense that they come directly from the differentiation rules that we know. Right, so they're obvious in the sense that we know the differentiation formulas, and once we know that we can do this, they follow immediately, right? We don't have to do we don't have to do any special work to kind of get these. So the first one is the one that we saw, the integral of x to the n dx is nx to the n, or sorry, that's the derivative, is x to the n plus 1 over n plus 1 plus a constant. I started writing the derivative. This is the one we just did, right? We started with x cubed was our first example, and then this one was like the general version of that, right? And this is true again, remember, because this is the general form of the family of antiderivatives for x to the n. And so that's the definition of the indefinite integral. The trig functions all follow as well. So the integral of cosine, for example, is sine of x plus a constant. And the integral of the sine of x is equal to the negative cosine of x plus c. Okay. And now keep in mind this negative, right? That's because if you recall, the derivative of cosine is negative sine. And so here we say the integral of sine is negative cosine. So there's kind of that negative sign has to be brought along. So these are the first couple. The next ones are, it may seem strange to define them, but again, the reason we kind of throw them up here right off the bat is because they follow directly from the trigonometric derivatives. And so the first one that's a little awkward is the integral of secant squared x dx. All right, you might say, well, what's the integral of secant? Well, we're not ready for that one because it's not a differentiation. There's not an obvious differentiation formula for it. So the integral of secant squared x dx is equal to the tangent of x, right? Plus the integration of the constant of integration. And so just to illustrate, so we call this one out, not because we're particularly interested in the integral of secant squared, but because it follows directly from derivative formulas. We call this one out because it follows directly from the fact that d dx of tangent of x is secant squared. And so therefore the integral of secant squared must be tangent, right? And that's sort of the wavelength we're on right now. We're not coming up with all of the deep integrals yet. We will get into those, don't worry. But we're just going to kind of pull these out just so that it's kind of clear where we're starting and what we already know. So the integral of secant x tangent x, that's equal to the secant plus the constant. And again, for the same reason, right? Because the derivative of secant is this. So the derivative of this guy is this guy, and so that's why we're calling it out. Another one that we kind of get for free here at the beginning is the cosecant. The derivative of cosecant actually squared. Okay. It's the negative cotangent. Okay, and we get that, right, because the derivative of cotangent is negative cosecant squared. Okay, one more trig integral, we get cosecant cotangent. Right, so that product, the integral of those two multiplied together, is negative cosecant x. And again, this one is because the derivative of cosecant is negative cosecant cotangent. Okay, that's the differentiation formula that we derived in Calc 1, and so we can use that fact to identify this integral. Here's a couple key ones. Integral of e to the x dx. What's that? Well, that one is e to the x plus c. Right, now you'll remember that the derivative of e to the x is e to the x, and so of course it follows that the integral, the indefinite integral of e to the x is itself plus some constant, right? So that one's fairly straightforward. Another one, the integral of a to the x dx. Right, so a is any positive real number, is equal to 1 over the natural log of a times a to the x plus a constant. Okay, now, so this one, let's talk about this one for a second, just to make sure that this is tracking. So where did this come from? Right, well, this is the antiderivative of a to the x. So what does that mean? It means that d dx of this value of this function, natural log of a to the x plus c, is equal to this. Well, how can we see that? Well, let's pull out the 1 over ln a, differentiate what's the derivative of a to the x. Well, you'll have to kind of, this is possibly one that slipped your mind because it doesn't get used a ton in Calculus 1. We don't use it a lot. But the derivative of a to the x is natural log of a times a to the x. Okay, and so that's where, you get the cancellation, and then you just end up with a to the x. And so that's why you have kind of this 1 over ln a in the front, right? So it's simply because the derivative is what it is, and so that forces the integral to be what it is. And the last one we'll mention, and we'll get into this one in more detail later, is the derivative of 1 over x dx. That's equal to the natural log of the absolute value of x plus a constant. Okay. And so why the absolute value? Well, remember, if we differentiate this, right, if we differentiate that, well, hold on. If we differentiate, if you recall our derivatives, if you differentiate the natural log of x, right, this is going to be equal to 1 over x, where x is a positive value. So you might remember that from your Calculus 1 when we started talking about this. And so this requirement that x be a positive value is why you have the absolute value plugged into this function here. Okay, all right, so that's kind of a quick list, right? So there we have 10 basic integrals, and we have a lot more than that, actually. If you think about it, like this one here, the integral of x to the n dx, together with item 4 here, this basically gets you all of the polynomials, right? So this is like the terms of a polynomial. So this fact, I guess, together with these two, right? Because you have a coefficient on front of each of the terms, perhaps, of the polynomial. But 3, 4, and then the first integration formula, that gets you, now you're able to integrate all of the polynomials, right? The entire space of polynomial functions. That's a lot of functions right off the bat, day one. Okay, so let's do some examples here. We'll kind of finish up this lecture with some nice examples. So let's see here. Let's calculate the following integrals. Let me start a new fresh piece of paper here. Fresh sheet. Let's calculate 1 over x cubed dx. Okay, let's do this one. So this guy, we would probably want to rewrite it as x to the negative third power, right? And then it's just an application of that x to the n formulation. And so the derivative here will be x to the negative 3 plus 1 divided by negative 3 plus 1 plus the constant of integration. And so what is all of that? Well, you get x to the negative 2 power divided by negative 2 plus the constant. And so you get basically 1 over 2x squared plus c. Right, so there's that indefinite integral. Okay, what about, let's try another one. These are good practice. What about the integral of the square root of x? What's that one look like? Well, similarly, you'd want to rewrite this so that it's x to the 1/2. Okay, and we can use that same rule, right? We'll say this will be x to the 1/2 plus 1 divided by 1/2 plus 1 plus a c. And we get x to the 3/2, right? Over 3/2, okay, otherwise known as 2x to the 3/2 over 3 plus c. Okay, so there's that one. Right, so sometimes integration feels a lot like differentiation. I mean, when you start to do some of these examples, you'll see, okay, a lot of the time integrals will follow very similar kinds of patterns. Right, certainly this example is a pattern. Right, this is basically the reverse of what the derivative looks like for the similar types of functions, for these functions. Here's another one. What about the integral of 2 times the sine of x? Okay, so here we can pull the 2 out, and so it's just the integral of sine of x dx. And so we know the integral of sine is negative cosine plus the constant, of course. Okay, and so then we would get, so kind of multiplying through the constant, you would get negative 2 cos x plus, and now here you would get 2 times c. So notice that 2c can be really any constant, right? So it's better, we don't usually like retain the 2 times c in these expressions. We would instead write this as just negative 2 cos x plus c. Just kind of like, technically you would want to distribute that 2 into the c, but then at the end you would say, well, a constant's a constant. It's a stand-in for a range of values, so there's no reason to write 2 times c. Regular, just plain old plus c is fine. Okay. Another example. As we did a lot of talking here, let's do some examples for a little while here. Let's just make sure we go through a bunch of these. Get our hands dirty here. So the integral of 3 over x dx. Well, this is 3 times the integral of 1 over x dx, right? And this is one we got, we pinned down just now. This is 3 times the natural log of absolute value of x plus c. Okay. Okay, something I didn't mention, right? Like, which I guess, I kind of did, but whenever you calculate these integrals, you can always check them by differentiating. Kind of like, when you were learning arithmetic, your teachers would implore, like, please check your work. Basically meaning, like, if you add a bunch of things together, you can subtract them to check it. Or if you divide two numbers, you can multiply to check them. So similar here, right? If you integrate a function, you'll get some other function. You can check it by differentiating it. So you can check that integral of 2 sine x dx equals negative 2 cos x plus c by differentiating. Right, so I could say d dx of negative 2 cos x plus c. Right, I can do that derivative, negative 2 d dx of cos x plus d dx of c, right? And, well, I can differentiate the cosine. I get negative 2 times negative sine plus 0, right? And so I get, what do I get? 2 sine, right? Which is what I have up there as well, right? So I can check those, right? And I can similarly check this one. Any of these that I've done, we can check. Can always check them. Okay, so kind of get into that habit. It's a good idea. I mean, it was a good idea when you were learning arithmetic. It just gets you comfortable with the idea that they're inverses, and it's also like a good way to check your work. But I suspect the reason teachers beg you to do it is because it helps you to really accept the idea that they are inverses of one another, and they have this relationship, and it's important. Just like when you were learning arithmetic, it was important that you understand that addition and subtraction are inverse operations. It's very important. Same with multiplication and division. If you can understand that, it helps you to develop like mathematical maturity. So even when you're here in calculus, it's the same kind of stuff. You really want to internalize this idea that they are inverses of one another, that they undo each other. A couple more examples. How about the integral of just dx? What does that even mean? Well, just like in algebra in general, what we mean here is 1 dx. So what is that integral? Well, it is x, right? Plus c. Okay. What about the integral of x plus 2 dx? Is this one, right? So this is going to play, use the fact that you can break these things up, the sum of two functions, right, x and 2. So this is the same as the integral of x dx plus the integral of 2 dx. And break them apart. And what do you get here? You get x squared over 2, right? So you get x squared over 2, and then technically plus c. And then over here you'd get the integral of 2x, or sorry, you get 2x plus c, okay? And so what happens there? Well, you can call this c1 and c2 technically. Right, and then so you'd get x squared over 2 plus 2x plus this c1 plus this c2. And now here again, the main reason for pulling this example out is to underscore the idea that you don't have to write c1 and c2. They're going to be added together, and so they're one constant, right? So really you'd want to write this as x squared over 2 plus 2x plus c. Okay. So hopefully that's clear. I know that when I first did calculus, I had to think about that for a second. Like, it isn't important that there are two constants, right? Because they're being added together. This form, x squared over 2 plus 2x plus c, is meant to be a general form, right? It's not specific. So the fact that c1 and c2, had to be added together to get to this third constant isn't important, right? The form is what's important at the end, right? That it's x squared over 2 plus 2x plus, whatever constant you want, right? And so that's why we kind of want to collapse those constants down to a single one. Otherwise, it could get ridiculous, right? Let's do one more example of those. So the integral of 3x to the fourth minus 5x squared plus x. Okay, similar to what we just did, right? It's going to be very similar. You can break this up into 3 different integrals. And so it'd be 3 times the integral of x to the fourth minus 5 times the integral of x squared plus the integral of x. Okay, so we can break it down just kind of like we did with derivatives and polynomials, basically the same properties. And so this would be 3 times x to the fifth over 5 minus 5 times x to the third over 3 plus x squared over 2, right? And then you'd have a plus c plus c plus c. Just put the c on the end, that's okay. All right, and then of course you could simplify this down, well, actually not really. So this would be 3/5 x to the fifth minus 5/3 x cubed plus 1/2 x squared plus c. So there's that integral. Now, if you differentiated this, you would get back to the original function. Okay, right? And you could probably just look at it and see that would be the case. If I were to differentiate this first term, for example, it'd be 3/5 times 5x to the fourth. Well, the 5's would cancel, and I'd have 3x to the fourth. That's where I get that. If I differentiate this next term, I have 5/3 times 3x squared, and the 3's would cancel, and I'd have 5x squared, and that's where you get that one, right? So you can kind of see it. Okay, good. Let's do maybe one more example, and then we'll call an end to this first lecture, which is kind of a long one. Let's integrate x plus 1 divided by the square root of x dx. So this guy here. Okay, and so the nice thing about this is you've got the numerator as a sum, so you can break this up as fractions. So you can look at it like this: x over the square root of x plus 1 over the square root of x. Right, that's just rewriting the integrand. But then you can break apart the integral like so. As well, right? And what's the benefit in doing that? Well, the benefit in doing that is you get a nice cancellation here, right? And so x divided by the square root of x is the square root of x, which is x to the 1/2. And then this is x to the negative 1/2. Okay. And then we can integrate this. So this would be x to the 1/2 plus 1 over 1/2 plus 1 plus x to the negative 1/2 plus 1 over negative 1/2 plus 1, and then plus c. All right, plus c for this. And when you do all of this, you get, well, for this front term, you would end up with 3/2 on the bottom, so that's 2/3 x to the 3/2. And then it's plus, because, well, oh, maybe it's minus. I think it's minus, actually. Minus 2, because this would be negative 1/2 plus 2 over 2, so it would be 1/2 on the bottom, which would be 2 on the top. Oh, sorry, it is plus, yeah. Plus 2, and then it'd be x, and that's negative 1/2 plus 2/2, so it'd be x to the 1/2. So altogether, you would have 2/3 x to the 3/2 plus 2x to the 1/2. I guess I kind of had that on the previous line, but felt like I should write it nicer. Oh, and you know, plus c, don't forget that, right? It doesn't make sense if you don't have the plus c, right? Definitionally, it's not right. So, okay, so that's a great place to stop with this lecture, right? So this is, again, this has been very much an introduction. So what did we talk about? We talked about what is an antiderivative, right? We talked about that. From that, we got this term indefinite integral. We saw that indefinite integrals are related to derivatives. Okay, and from that relationship, we basically that relationship implies a bunch of integrals. Okay, so that's sort of, I mean, a lot of ground. Admittedly, this is a big section to talk through. So we covered a lot of ground there. So not surprising, it's a longer lecture. But okay, now next time we'll get into we'll begin, the section will be called area, and we're going to be talking about integration and its relationship to the area problem. The problem of finding the area under an arbitrary curve. Okay, and so that again will be a challenging lecture, but I think it'll be it's one of my favorite sections from all of calculus, so I think you'll probably enjoy it as well. All right, so we'll leave it at that, and we'll talk to you next time.